So this is shear example 4, continued, page 4. So so in this bit here, we're going to be trying to calculate the maximum shear stress in the beam. So let's just draw out the beam. So we're going to assume it's a simply supported beam, and we're going to assume that there's been some load applied to the beam, and that the shear force going up at the reaction is going to be 1750 kilonewtons. So now if we pretend that we're going to make a cut here, so we're going to make a cut there, and then if we draw out the beam again at the position of the cut, there would be a vertical shear force which would give rise to some shear stresses flowing or going down the depth of the web. And if we wanted to do a plot of the shear stresses, we would need to remember that it ought to be calculated relative to the neutral axis if we wanted to use the equation that's been provided, and we would probably know that the shear stress would be 0 at the two tops. It would come down like there. Then because it's a stress and stress is force over area, the cross-sectional area suddenly changes down there, and then would probably have something like there. So if I put that tau, and remember the units of y is in millimeters going upwards, and the units of tau is a stress, which is force over area, so that's newtons per millimeter squared, and then that value there is going to be tau max. Now, if you recall the cross-sectional shape of the section, so let's just draw the cross-sectional shape up there. So we've got two relatively thin web members compared to the thicker thicker plate at the top. Now, the equation is going to be tau. So we've got tau y is going to be equal to the shear force V multiplied by S dash y, and that needs to be divided by I, and that needs to be multiplied by B, which is also a function of y. So from there we could say tau max is equal to the value of tau when y is going to be equal to 0 millimeters, is going to be equal to V times S dash calculated when y is 0 divided by I times B times y, B when y is 0, which is right at the center. Now going back to the cross section, hopefully you should realize that in terms of applying that equation, let's say that the web the two web members were moved to the center and they were actually touching each other, you should realize that the calculation shouldn't be affected by the position of these two members or these two web members relative to each other, because there's nothing in the formula that considers their distance apart. Therefore, it should be clear that by must be 2 times the web, so that whole thing is going to be b of 0 must be equal to 2 times 12 millimeters, since the thickness of each web member is 12 millimeters, so that's going to be 24 millimeters. V in this case here is going to be 1750 kilonewton meters, and then I for the composite section we have already calculated as being 1.361 times 10 to the 9 millimeters to the 4th. So all we have left to do is to calculate this S-0. So let's do that as an aside. So we have the neutral axis. So let's draw out the section. So we'll draw out the section like there, and then with these two bits going down, and then these two bits, these two web members going down, and then that's going to be the neutral axis, and therefore our y must be calculated relative to the neutral axis. So we want to find out what the shear stress is at the neutral axis, which means that when we apply the equation, we effectively want to work out the first moment of area of that. Okay, so you could also work out the first moment of area of everything above the neutral axis, but that will work out to be the first moment of area of everything above the neutral axis, so because of symmetry. So take either one if you're confused, but they should both work out to be the same. So we want to work out the first moment of area relative to the neutral axis, or when y is equal to 0. So to work that out, we've got our areas A1. So we've got our area A1, and we calculated the area of A1 was going to be the breadth times, the breadth of the section, so that was going to work out to be 600, 6 times 10 to the 3 millimeters squared. And then this area here is going to be, that's going to be area A2 over 2, because before when we calculated A2 we assumed that A2 was the whole depth of the web. So that's going to be half the area, and that's also going to be the area A2 over 2. So that area is going to be equal to 3.36 times 10 to the 3 millimeters squared. So to work out the first moment of area about the neutral axis, so we'll have we'll have S dash at 0. So that's going to be 6 times 10 to the 3 millimeters squared, and that needs to be multiplied by the distance to the centroid of the top bit. So draw a dotted line across there, and then we know that the total depth is going to be 300 millimeters, and we know that the thickness of the top plate is 10 millimeters, so that distance there is going to be 290 millimeters. And then we need to add onto that bit there the area 3.36 times 10 to the 3 millimeters squared, and that needs to be multiplied by the position of the centroid there of that area, and that one is going to be 140 millimeters. So that distance there is going to be 140 millimeters. So 600 minus 40, 600 being the total depth, minus 40 is going to be 560. 560 divided by 2 is going to be 280, and 280 divided by 2 is going to be the 140, so that confirms that. And we need then to add on another one for this area there, but that's going to be identical, so I'm just going to put a 2 times in front, and then if you bang that through the calculator, the whole lot S-0 is going to work out to be 2.681 times 10 to the 6 millimeters cubed. So we'll now substitute that 2.681 times 10 to the 6 millimeters cubed, and then put all those values in, and we will get a shear stress has been calculated as being 143.644 newtons per millimeter squared. So that would be how to calculate that value of Tmax, and that value of Tmax, the maximum shear stress, is going to be 143.644 newtons per millimeter squared. So that shear stress would be flowing down both of the webs. Sorry, not flowing, but both. That shear stress would be acting downwards at both of the webs, and then to convert that into a traction per web, you would do 143.64 multiplied by the thickness of each web, which would be 12 millimeters. And that would work out, if you wanted to, the traction or the force per millimeter flowing down the web at the point of the cut. But all I'm trying to say is that that stress, 143.644 newtons per millimeter squared, that is applied to both webs if you wanted to turn that shear stress into a force. And remember, at the start here we had 2 times 12 millimeters for our value of B.